This is Bob Capetta from the College of the Florida Keys, and this lesson is on the cross product. So we're given two vectors, the vector u, which is 1, negative 4, 3, and the vector v, which is negative 2, 1, negative 5. These vectors are both in 3 space, and my goal is to construct a vector that is orthogonal to both of them. We're going to answer that question by using the cross product. And this is going to be our strategy. The vector u cross v is the determinant of the ijk vectors across the top row, the u vector 1, negative 4, 3 in the second row, and the v vector negative 2, 1, negative 5 in the third row. As we expand out this matrix, we will get a vector orthogonal to both u and v. Now, how does that work? We're going to put plus, minus, plus across the top. So it's plus I minus j plus k. I's minor, cross out the column, cross out the row, and we get negative 4, 3, 1, negative 5. J's minor, cross out the column, cross out the row, 1, 3, negative 2, negative 5. K's minor, cross out the column, cross out the row, 1, negative 4, negative 2, 1. And next we have to evaluate all of these determinants. Here, negative 4 times negative 5 minus 1 times 3. Here, 1 times negative 5 minus negative 2 times 3. Here, 1 times 1 minus negative 2 times 4. So negative 4 times negative 5, 20, minus 1 times 3 is in the first slot. Negative 5, 1 times negative 5, negative 5 minus negative 2 times 3 minus negative 6, negative 5 minus negative 6 here. Be careful of this minus, and remember it's plus, minus, plus across the top. And then 1 times 1 is 1, negative 2 times negative 4 is 8, 1 minus 8 in the third slot. So we get 20 minus 3 is 17 here. Negative 5 minus negative 6 is negative 5 plus 6, or 1, but with the minus sign there becomes minus 1j. 1 minus 8 becomes negative 7k. So that our result for u cross v is I times 17 minus j times 1 plus k times negative 7. I prefer to write vectors either in angle brackets or in columns. So I'm going to go ahead and rewrite it this way and say it is 17, negative 1, negative 7. Now I should check that. Remember, it was supposed to be orthogonal to both u and v. How do we determine if vectors are orthogonal? Take their dot products. The dot product must be 0 if two vectors are orthogonal. So we're going to indeed check the dot product with u cross v together with both u and v. So starting with u, what's the dot product of u with u cross v? Well, u dot product with u cross v, 1 times 17 plus negative 4 times negative 1 plus 3 times negative 7. 1 times 17 is 17. Negative 4 times negative 1 is positive 4. 3 times negative 7 is negative 21. So 17 plus 4 minus 21, 21 minus 21 is going to be 0, which of course is correct. So that proves that u and u cross v are orthogonal. We constructed u cross v to be orthogonal to both u and v, but I've at least checked that it's orthogonal with u. I have to do the same thing with v to make sure that I've done it correctly. So this time I'm going to take the dot product to see if u cross v is orthogonal to v. So v dot u cross v, negative 2 times 17 is negative 34. 1 times negative 1 is negative 1. Negative 5 times negative 7 is positive 35. Certainly negative 35 plus positive 35 is 0. And yes, indeed, v and u cross v are orthogonal since the dot product is 0. So we have been successful with that. All right, so we've done u cross v. I want to take a look at v cross u. So you saw our process. We put ijk across the top row, and then we put the first vector in the second row and the second vector in the third row. So if I do v cross u, I've got to do negative 2, 1, negative 5 in the second row, and 1, negative 4, 3 in the third row. So you'll see that second row, negative 2, 1, negative 5. Third row, 1, negative 4, 3. Second row is v, third row is u, because the order is v cross u. So the question is u cross v the same as v cross u? Well, let's go through our process. I times his minor minus j times his minor plus k times his minor. Remember, plus, minus, plus across the top. I's minor, cross out the row, cross out the column. 1, negative 5, negative 4, 3. Minus j, cross out the column, cross out the row. Negative 2, negative 5, 1, 3. Plus k, cross out the column, cross out the row. Negative 2, 1, 1, negative 4. So what do we get here? 1 times 3 is 3. Negative 4 times negative 5 is 23 minus 20. Negative 2 times 3, negative 6, minus 1 times negative 5, minus negative 5 here. Negative 2 times negative 4, positive 8, minus 1 times 1 is 1. 3 minus 20, negative 17. Negative 6 minus negative 5 is negative 6 plus 5, negative 1. But with this minus sign, it's going to become positive 1. Then 8 minus 1 is plus 7k. Now this is v cross u. Notice u cross v was 17, negative 1, negative 7. V cross u is negative 17, 1, 7. They are certainly related, but they're not the same. But how are u cross v and v cross u related? Well, first let's state that the cross product is not commutative. U cross v was not the same as v cross u. But what they are opposites. So this is a rule that we can use. U cross v is the opposite of v cross u. All right, I want to do another example. Construct a vector orthogonal to both u, which is 5, negative 3, negative 2, and v is negative 1, 4, 7. So the choice is to go ahead and do u cross v. Top row, ijk. Second row, first vector, 5, negative 3, negative 2. Third row, second vector, negative 1, 4, 7. Plus minus plus across the top. Plus 1 times his minor, minus j times his minor, plus k times his minor. I's minor, cross out the column, cross out the row. Negative 3, negative 2, 4, 7. J's minor, cross out the column, cross out the row. 5, negative 2, negative 1, 7. K's minor, cross out the column, cross out the row. 5, negative 3, negative 1, 4. So we get negative 3 times 7, negative 21, minus negative 8 here. We get 35 minus positive 2 here. We get 20 minus 3 here. Negative 21 minus negative 8 is negative 21 plus 8, or negative 13. 35 minus 2 is 33. 20 minus 3 is 17. But notice, the 33 has to become negative because it always goes plus minus plus. The sign on j is minus 1 times what follows. So we get negative 13i minus 33j plus 17k. We think that's u cross v. Do a quick check. What do we get with u? U dot product with u cross v. Negative 65 plus 99 minus 34. That indeed is 0. So that checks. And let's try v dot product with u cross v. Again, we hope that we get an answer of 0. And v is negative 147 dot product with negative 13, negative 33, 17, our version of u cross v. 13 minus 132, 4 times negative 33 is negative 132. 7 times 17, 119. Indeed, 132 minus 132 gives me 0. So u cross v was orthogonal to u, it was orthogonal to v. Check, check. And that is correct. We have indeed constructed a vector orthogonal to both u and v. Now let's look at the geometry here. I have a vector in 3 space u, I have a vector in 3 space v. U cross v is orthogonal to both u and v. So u cross v points in this direction. V cross u would be pointing in the opposite direction, pointing down. But notice u cross v is perpendicular to both u and v. I'm going to call theta the angle between u and v, and notice what I've written here. The magnitude, or the size, of the vector u cross v. And what we'll say is the magnitude of u cross v represents the area of the parallelogram spanned by those vectors. So this is the vector u, this is the vector v. Since it's a parallelogram, this is also the vector u, and this is also the vector v. Parallelogram has 4 sides, so the vectors are repeated. So again, we can see u cross v is here, but the magnitude of u cross v will tell us the area of that parallelogram. So let's think about the geometry here. What will that area of that parallelogram be? So here's my 2 vectors, u and v, arrow here for u, arrow here for v. Keep that in mind. We know the area of a parallelogram is base times height, so the base is the magnitude of v, the magnitude of u. The height is not the magnitude of v. The height is here. It's perpendicular from the base up to the top part of the parallelogram. So I need to figure out what the height is. So the base will be the magnitude of u, and the height will be that distance. So how can I determine the height? Well, I need that angle again, which I called theta, and I need this side, which is the other vector v, but I'm interested in its length. So looking at this triangle, the sine of theta is opposite over hypotenuse. So the sine of theta is the height of the parallelogram, also the altitude of the triangle, divided by the hypotenuse, divided by the magnitude of v. If that's the case, multiplying both sides by the magnitude of v, we get the magnitude of v times the sine of theta is the height of this parallelogram, which means I can substitute the magnitude of v times the sine of theta into this formula for the area of the parallelogram. But what did we say in our previous picture? If we go back to the picture, it said that the area of the parallelogram was the magnitude of u cross v. Well, what have we done? We've determined the magnitude of the parallelogram as magnitude of u, magnitude of v sine theta, which will then give us a rule that the magnitude of u cross v is mag u, mag v sine theta. Notice that sounds kind of familiar to u dot v, which was mag u, mag v cos theta. So let's do an example of that. I've got vector u, which is 1, 4, negative 1, and vector v, which is 3, negative 5, 4, and my goal is to find the area of the parallelogram. To do that, I've got to find the cross product and then find its magnitude. So the cross product, u cross v, ijk across the top, plus minus plus, of course. Second row u, 1, 4, negative 1. Third row, 3, negative 5, 4. So plus I times his minor, minus j times his minor, plus k times his minor. I's minor, cross out the column, cross out the row, 4, negative 1, negative 5, 4. J's minor, cross out the column, cross out the row, 1, negative 1, 3, 4. K's minor, cross out the column, cross out the row, 1, 4, 3, negative 5. Then here I get 16. 4 times 4 is 16. Negative 5 times negative 1 is 5. 16 minus 5 here. Second one, 4 minus negative 3. 4 times 1 is 4. 3 times negative 1, negative 3. 4 minus negative 3 will be 7. Here, 1 times negative 5. Negative 5 minus 12 will be negative 17. Again, 16 minus 5, 11i. 4 minus negative 3 is 7, but I've got this minus sign there that'll become minus 7j, and then minus 17k. So I have determined a vector orthogonal to both u and v. We've got this vector u cross v. Always a good idea to do a quick mental check. 1 times 11 is 11. 4 times negative 7 is negative 28. So 11 minus 28 would be negative 17. Plus positive 17 is 0. That checks nicely. 3 times 11 is 33. Negative 5 times negative 7 is 35. Add those together, I get 68. 4 times negative 17 is negative 68. Indeed, u cross v is orthogonal to both u and v. But what I wanted here was the area of the parallelogram. The area of the parallelogram is going to be the magnitude of u cross v. So here's uv and there's u cross v. Area of the parallelogram is the magnitude of u cross v, which will be the square root of the dot product of this with itself. So this dotted with itself is 11 times 11, negative set plus negative 7 times negative 7 plus negative 17 times negative 17. Or if you like, you can think of it as Pythagoras, square root of 11 squared plus negative 7 squared plus negative 17 squared, which is the square root of 121 plus 49 plus 289, or the square root of 459. And you'll notice 9 goes into 459. And we get our answer of 3 times the square root of 51, which will be the area of the parallelogram. And that will conclude this lesson.